Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you. Good morning, and thanks everybody for coming. Today we have another rising star from UW's Rising Star Factory this year, Colin Dixon. Some of you may actually know him. He spent a summer with us and then some change, and he's going to tell us about how we should look at networks as programmable platforms rather than computers, individual computers as programmable platforms. Good way. Yeah.
It's close enough. So thanks for the wonderful introduction, Ratul. So as he said, today I'm going to talk about the network as a platform, and it is basically how we should think about programming our networks as a single object rather than a bunch of proprietary little objects that do their own thing on their own. And so I'm going to start off by PowerPoint disagreeing with me. Let's see. There we go. I'm going to start off talking by way of analogy about cell phones. And so if you think back, sort of way back to 5 years ago, before the iPhone came out, before the Android came out, before finally the Windows Phone came out, you remember your phone was basically basically something you bought. It made phone calls. It might have had a calendar that you never used because you had to press the stupid little buttons 7 times in order to get each letter. But it was sort of the phone that you got and you kept for the entire time you had that phone. It wasn't going to change. It wasn't going to add new features. And then all of a sudden, things started to really shift. And it's sort of hard to even remember what it was like before this, but I'm sure all of you have one of the devices at the bottom, either an Android or a Windows Phone, probably at least half Windows Phones, I'm thinking, in your pocket, which is just a radically different kind of object. I actually do have my Windows Phone, just so that way I'm off the hook for making jokes. It sort of radically shifted. These phones are not things which have only the functionality that you buy them with. They have applications which you can install and run, and they've sort of brought about a radical wave of innovation. And sort of what changed? These old phones were actually pretty decent. They had not terrible processors in them. They had data connection that almost worked. The functionality wasn't really missing. What was missing was the extensibility. It was very hard for anybody except for a very small subset of people to add functionality to them. Nobody could write apps for them. Nobody could do that. And so what happened was phones became a platform. A couple of companies got together and decided they were going to try and make it easy to build applications, easy to get those applications out to lots of different people. And this fostered a huge wave of innovation, and as a process, sort of made cell phones what are likely the dominant computing platform for the next 10, 15 years. And so the question I'm going to hope to answer in this talk is, can we do something similar for networks? And in particular, I'm going to talk about 2 different kinds of networks. First, I'm going to talk about networks of electronic devices in homes. So things like light switches, doorbells, cameras, televisions, that kind of thing. And second, about networks of computers and enterprises. So can we turn these into sort of an extensible, programmable platform where we can enable the same degree of innovation? And this raises a bunch of challenges because networks aren't phones. They have a whole lot of very different properties that you're going to have to deal with. First of all, you have to coordinate many different devices to carry out some kind of centralized task. And to do this, we're going to treat the network as a distributed system. And we're going to try and use standard distributed system techniques in order to cause them to basically carry out a given task together without having to worry about doing different things in different places. Second, we need to overcome the limited extensibility of a bunch of these different devices. If you're talking about trying to write a program that runs on a light switch, you're not going to run a program on a light switch. So you're going to need some way of thinking like you could program them even though you can't. And so we're going to proxy these devices with sort of general purpose hardware in order to give us a uniform platform that looks kind of the same everywhere. And lastly, we need simple abstractions and APIs. We actually want this to be a platform. We need to make it easy to write applications and get them to run on top of it. And so we're going to build 2 different sets of APIs, one in the home and one in enterprise networks. And sort of just as a proof of concept, you can build these APIs. So the key idea of this talk is we want to provide an extensible software platform on top of heterogeneous network hardware to enable people to build new and interesting applications easily. And this includes all the things that you might expect from a platform. Here, people probably have a better idea of what a platform means than they do the rest of the places I'm giving this talk. But basically, you need an abstraction layer so that you can think about the particular devices, some kind of security model, a programming model of what you can think of. So the standard things you think of what you're programming against when you write an application. And I'm going to talk about this in the context of two systems that I've built. The first one is work done here with some of the people that are in this room called HomeOS. And its goal is to make it easy to build cross-device applications in the home. So make it easy to write things that coordinate different devices all across your home, and also make it easier for home users to manage that technology, to easily bring in innovative applications and new functionality into their home. And the second thing I'm going to talk about is ETTM, which is focused on how do you make it easier to run and provide the interesting services that you would like from your enterprise network. And doing so by running these network control on end hosts on your network, rather than running it with proprietary middle boxes in the middle. So the basic outline of my talk, I've finished up sort of with the introduction and motivation. I'm going to talk about HomeOS first, and then end to the middle. And then I'll move on to related work, and I'll conclude, and I'll take your questions. Also, if you have a really burning question you want to ask it in the middle, you can interrupt me, and I'll decide whether I like you or not. So I'm going to start off with HomeOS just by bringing up how much technology has made its way into modern homes. So there's a huge amount of technology. You probably recognize all of the devices up here, or almost all of them. You probably have something like half of them in your house, from locks to smartphones to laptops to cameras to televisions to access points, gaming systems, tablets. There's just this huge amount of technology that's migrated its way into homes. And increasingly, it's connected or programmable in some way. At least you should theoretically be able to reach out and tell it to do things or ask what it's currently doing. But we find that despite that, home users are struggling with technology in their home. And for two key reasons. The first reason is that there's a management nightmare around each device has its own interface, its own semantics, its own particular details that you need to configure. And you need to make sure you understand that and do it for each device. And since you expect that maybe the number of devices in your home is doubling every 2 years, you're not going to have twice as much time to manage your home every 2 years. Imagine you're putting a Wi-Fi chip in everything, John. So you're going to have a number of Wi-Fi chips and devices in your home doubling every 2 years. That seems like it's been happening for the past 5 or 6 years. And so the second problem is integration hurdles, which is that even if you have these devices and they could theoretically talk to each other, in practice, getting different systems to talk to each other is very difficult. So you might get lucky and your Xbox and your Windows computer and your Zune all play nice together. But if you want that to talk to your ADT security systems, that way you can use your Windows phone to view your cameras, that's unlikely to work very well. So even when you do get these sort of islands of connectivity, getting them to talk to each other is very difficult. And so it makes building things that you might kind of like hard. And so in this example, let's say that you have a digitally controlled door lock, which you can buy from Schlage today, a doorbell that's connected and will send a signal when it's been rung, and a security system with a camera. It would be really nice if I was going to be out and about during the day and I knew somebody was going to come over and visit, that I could have it set up so that way when they rang the doorbell, it would take a picture of who was at the door, send it to my phone, and I would say, oh, it's Ratul. I'm expecting Ratul to come over today. It would actually ask me if I wanted to unlock the door for him. I would say yes. It would reach back and unlock the door, and Ratul will be able to come in. And this is something which I just described in like 60 seconds. But I'm sure that you can imagine why it is that this might be difficult to build. I'm going to step through it. So imagine it was somebody you liked better than Ratul.
Your mom, she just showed up.
Yeah.
Visit.
But just the idea is, you should be able to imagine it's the babysitter that's coming over and you want to let them in. You don't want to give them a key. So you might imagine, since this is actually...
You really don't have a You want to trust your babysitter, but you don't want too much.
Anyway, so you might imagine that sort of with all this technology coming into homes and the fact that people seem to have trouble exposing it, the developers would help and build the kinds of applications that I just went through and described. But developers you don't know a whole lot of people that are writing apps for the home. It's not like you hear about this huge home systems development things. You hear about iPhone apps, you hear about Windows apps, you hear about that. And so there's some good reasons for that. So basically, right today, you have to write an application on top of the hardware. There's almost no support in between you and the hardware. And this involves dealing with a whole set of problems in terms of heterogeneity in the home. So first, you have to worry about topology. You have to worry about, well, how am I actually connecting to each individual device? Is it on Wi-Fi? Is it on 3G? Is it on Zigbee or Z-Wave? And even different subnets within the home. And even if you deal with that, you then need to deal with the actual diversity of devices. So there's 100 different kinds of cameras in the world, and each one of them has a slightly different interface, or a radically different interface. So you actually need to be able to speak the same language as the device. And then if you've done that, you might not be able to assume that you're the only application running in the home. You probably can't. So what do you do if the security application is set to say all of the doors and windows should stay closed and locked when there aren't people left in the home, but the climate control application says it's a nice day outside, we could save energy by opening the windows. You need some way to manage these conflicts and these coordination issues. And implementing that per application seems pretty difficult. And then even if you've done all that right, different users want to do different things with their homes. So you have to somehow express all of the preferences that any user using your application would like in some reasonable way so that way they can do it. And then when you're done with all of that, you can write the 12 lines of code that you actually wanted to write at the beginning that constitutes the actual application logic of when the doorbell rings, take a picture, send it to the phone, ask them if they unlock the door, and if they say yes, actually unlock it. And that's, and then you can finally write those 12 lines of code. And sort of to add insult to injury, all of this stuff is application agnostic. There's nothing in particular about the unlocking the door application that required that I have all of these pieces. It's just a property of trying to write an application in the home. And so you can sort of start to get an idea why developers aren't helping. Developers have this huge mountain of work they have to do for themselves in order to get anything to work. So you might say, well, what about device vendors? They're the people that are actually making the devices. A bunch of the problems I just talked about were having to do with device, the particulars of devices. They already know what it is. They probably already have drivers for them. And vendors don't seem to be helping either. They seem to be building only islands of sort of usefulness. So Schlage makes a door lock. They make an iPhone app. That's it. They don't try and communicate with other devices, try and use other people's things. And when they do try and make use of other people's devices and integrate, they run into sort of the same issues I just talked about. How do you actually coordinate with the other devices in the home? How do you expose the functionality in a way that you can make sure that different users can express their preferences? And lastly, you might think that, well, maybe one vendor was going to take over, but no single vendor is likely to control the devices in your home in the near future. And you can imagine this probably isn't going to be true ever. You probably don't want Apple or Microsoft making your stove, for instance. It's just not their area of expertise. And so we're not the first people to sort of note that we have this problem of this massive number of devices and no really good way to try and get them to work together. And there's been sort of two approaches to trying to solve this problem. The first is interoperability. And interoperability, even if it did happen in entirety, isn't sufficient. And so you can imagine all devices could pairwise communicate with each other. This would make it possible to go and build applications that might coordinate a couple different devices in order to do something useful. But it's still not going to solve the higher issues of preferences and also coordination. So imagine if you had a camera-based entry system and a remote lock application. How are they going to multi-share the lock? How are they actually going to figure out who should have access to it? Who should get to take the final say? And so you still need to build these separate uses. So we make lots of use of interoperability protocols in what we end up building, but they really don't help you build a complete system for how it is that you write applications that would run in the home. At the other end, we have monolithic systems. These are things like security systems, entertainment systems, and they're sort of commercial home automation systems. And these systems they're just inextensible. Unless you buy the particular hardware that they want you to buy, you end up not being able to extend the system, and the set of applications that you get to run are limited by what you have. And if you want to try and combine two of these systems together, like your security system with your stereo system, say you want to look at your security camera on your smartphone, getting these two things to talk to each other is usually very difficult, and it's often just above the pain threshold of what you're willing to do, even if it is technically possible. And so we're proposing an alternative approach of a home-wide operating system, where the operating system will run on top of all the devices, logically talk to all of these devices and bring them together into one place, where they can mediate access to those devices on behalf of applications. And furthermore, if you have this central place, you can give users one place to control the technology, which is in their homes, and actually express their preferences to how things should work. And you can even couple this with an application store or a marketplace that would let you say, this application is compatible with your home versus this one isn't, or suggest other people like applications that are like this. If you bought this device, it would enable a bunch of new applications. And so we think this is a much more compelling way to try and think about solving the problem. And it's going to leverage the interoperability and the other ideas, but it's going to end up with something that looks quite different. So in building HomeOS, we've had three main goals, and these correspond to sort of the three stakeholders in the home ecosystem. The first is that the thesis of HomeOS is that the way to expose functionality and new features to homeowners is through applications. And so we want to make it really easy for developers to build new applications for the home and get them out to people. So the first goal is really to simplify application development, make it easy for people to write cool applications and get them in the hands of homeowners. Second, in order to make things easy to program, we have to standardize things a little bit. And you run the risk whenever you standardize things of shooting yourself in the foot by preventing new devices from working with what you have, maybe making it so that way device vendors can't differentiate their devices from other people's. So the second goal is for device vendors, we really want to make it easy to build new features into your device or totally new devices and rapidly expose that functionality up to application developers. And lastly, none of this is going to matter if we can't simplify the tasks of users managing the technology in their homes. So if you can't simplify user management of technology, none of this is going to work. So the third thing is really focus on trying to cater what users want out of their homes and make sure the tasks which they want to carry out are easy to do. So I'm going to step through each of these goals and explain sort of how we satisfied them with HomeOS. I'm going to start off with simplifying application development. And I'm going to walk through sort of each of the difficulties I mentioned that developers have with building applications in the home one at a time and build up the pieces that we've made to make this easy. So first, to deal with topology differences, we use drivers. This is nothing new, but we use drivers to logically bring the devices across the network to one location where we can program them as though they were directly connected to a single PC. In order to deal with the differences between devices, we have drivers export the functionality at a functional layer via services. And I'll come back to services a little bit on the next slide and explain what I mean there. To deal with coordination issues of which applications get to control which devices at what times, we build an access control layer so that we can make principal decisions about which accesses are allowed and which accesses aren't and why. And lastly, to deal with user preferences, we give users a management user interface in order to control the access rules in their house. So what accesses are legal and what aren't, and under what circumstances. And this is how we give users control over what applications are allowed to do in their house and to what devices and sort of at what times. And this is our model for how it is that we give users control over what happens in their homes. So I said I would come back to services, and I will, and I would right now. Services are what programmers develop against. And so services export functional descriptions. So these drivers are functional descriptions called roles. Roles are things like light switches, televisions, displays, speakers, etc. And you have functions on them. We call them operations, like lightswitch.invoke, or like lightswitch.turn-on, lightswitch.turn-off, that kind of thing. And application developers program against these. But anybody who wants to can make a new role. And this enables vendors to innovate and differentiate their products. So if somebody comes out with a brand new kind of strange device, they can invent a new role for it and rapidly expose that functionality up to developers to program against. Or if Sony wants to expose the cool new features of their Sony Bravia TV as opposed to Vizio's baseline TV, they can actually make that kind of decision. And they can say, here's the new extensions that enable you to make use of these cool features. And this enables us to allow vendors to rapidly bring new features to market and expose them up to developers at the same time as sort of letting commodity vendors actually produce inexpensive devices and get them out there so you can have the basic functionality. And lastly, in order to simplify user management tasks, you actually need to know what users want to do in their homes. And so a bunch of my colleagues here at Microsoft did field studies of modern homes in order to try and get an idea of what people with technology in their homes do with it, and with extensive sort of home automation technology. And there's a whole bunch of takeaways from this. There's a whole Chi paper about it, which I suggest you go read if you're interested. But the three takeaways from a systems building perspective, in particular for access control rules, which is how we give users preference, the first one is that users want applications as security principles. And this is coming to be true in sort of modern smartphone OSs, but it's less true in commodity OSs today. And it's a different approach. Second, users want to talk about time in access control decisions. And this is for two reasons. The first reason is they always want to talk about guests. They want to invite people into their home and give them some permissions, but not all of them. Whether it's a house guest or somebody coming to do work on the house, they want to be able to say, we're going to give you some permissions for this limited window of time, and then it's going to go away, and I won't have to worry about it anymore. And the second thing is for parental controls, which is that you don't want kids playing Xbox after 11 o'clock at night, that kind of thing. And lastly, and this is the most interesting to me, users are actually much better at configuring things than they think that they are. But they're very bad at convincing themselves that they've done it correctly. And so giving users a way to be able to say, figure out, did I configure it the way that I wanted to configure it, is critical for them to actually have confidence in their configuration and thus trust the system in order to do what they wanted it to do. And so when we built our management primitives, we kept these sort of three things in mind. So the first thing, which we sort of built from the ground up, is reliable reverse perspectives to build confidence. And this is the ability to ask questions like, which applications can open the front door? And actually be able to give a concrete answer to that question. And in modern sort of operating system access control systems with dynamic delegation, this is a very hard question to ask. Asking, give me a list of all the people that can open, system.conf is going to be a difficult question to answer. And so we've restricted our set of access control rules to being positive things of the form user can access device using application within a certain window of time. And this enables us to do these reverse queries very quickly and easily and be able to let users build confidence. In addition to specifying time and access control rules, users actually have validity time windows to enable guests, which is something we found many people wanted. And you might imagine that requiring people to specify access control rules for every user, for every application, for every device would be difficult. But we make, because of this n-cubed problem, but we make this pretty easy by using application manifests. So applications specify the devices they require in addition to the devices that they can use in any way, shape, or form. So we can radically constrain the number of possible rules that make sense in the system. Your music player application isn't going to be able to get access to your front door lock just because it doesn't make sense. And so we've actually built this. It's about 15,000 lines of C# that run on top of the .NET CLR. Only about 2,500 lines of this are in the kernel, which has to do with mapping roles and services back and forth. The rest of the code is in applications and drivers. We have built 11 applications, although it might be more by now. We've been continuing to work on this stuff. And two example applications of the kinds of things that we've been building are music follows the lights, which is basically where the lights are on, you play music. When the lights are off, you don't play music, and you can transfer it back and forth. This is just using lights as a proxy for where people are in the house. You can imagine using motion detectors or something else as they became available. And the second thing we built is a two-factor authentication program, which uses a spoken password and face recognition in order to grant access to either open your front door or disable parental controls or that kind of thing. And you can see our test bed here on the right. It consists of a couple of laptops, some programmable lamps that have dimmer switches attached to them, smartphones, a camera, a television. We now have a door opening and closing sensor and a couple other things. And so now that we've actually built it, this is at least technically a systems talk. So I need to give you some kind of CDF of performance. So the top graph on the right here you can see is basically a function of latency for a service invocation operation invocation, which is something like lightswitch.turnOn. And what you can see is it's the latency as a function of the rate of operation invocations per second. And it's both for using application domains as an isolation mechanism to isolate applications from the kernel and with no isolation whatsoever. And what you can see is that with no isolation, we can support about 10,000 operations per second on a commodity PC. With isolation, it's about 8,000, and it stays somewhere under a millisecond in order to do one of these operations, regardless of how fast you seem to do them. And so this seems pretty reasonable, but this is just for one application querying one device. And so the second graph is showing what happens to latency as you increase the number of applications and devices. So for each number of applications, we have for each application, we have 4 devices, and the application queries each of those 4 devices 10 times per second. So this is about 40 operations per second per application. So with 100 applications, you're talking about having 100 applications querying 400 devices, each 10 times per second, about 4,000 operations per second overall. And you still see it's about 5.5 milliseconds in order to do an operation, and on average, and the vast majority of them fall less than 10. And so with interactive guidelines of about 100 milliseconds, you can do somewhere between 10 and 20 of these things serially, and many, many more than that in parallel. And so we think this works pretty well for small businesses and homes. If you wanted to make this work for the Sears Tower, you might have to think a little bit about how we would change things. Did you have a question?
You said you need to write some drivers. Did you write the drivers in C#?
It depends on the driver. So some of the drivers, yes. Others of the drivers, we wrapped existing Windows drivers in C# so that way we can make calls to it. So for instance, we use Z-Wave lamps. So there's a Z-Wave driver that's written in native code, which we have a C# wrapper to. But in the case of webcams, we actually have a pure C# wrapper that goes out and makes queries against the web interface of the camera. So it depends.
Most of these devices are going to be wired or wireless or random combination. I'm just wondering if you can put this in context. It seems like querying anything thousands of times per second over a wireless link isn't going to happen anyway. So I'm wondering if this is ever actually the bottleneck in its real deployment.
My goal with this graph was to demonstrate that we aren't the bottleneck, and I think that that's probably what this does. So I think you're right. I think you're exactly right, which is to say that the bottleneck is going to be getting out across a wireless link to get to a camera, or getting over across Z-Wave to go somewhere. So we're expecting a random smattering of connectivity options, probably increasingly wireless and increasingly less wired. And so this actually is a dummy driver. There's no actual device involved in this top graph. It's just going out to ask it. If you actually need to go get an image from the camera, right now the web interface is kind of slow, so it takes almost a second in order to get back with an actual picture from the camera. And that's just sort of an artifact of the particular hardware that you're running on top of. But we also don't feel like the environment of the home, if it takes a second to get a picture of the front door, that's probably okay. You probably don't need nanosecond sort of high frequency trading style performance in the home.
Would you ever actually want to query a device hundreds of times per second as opposed to having some sort of notification interface?
We have notification interface as well. This was sort of just to test the application boundary crossing and what the performance implications of that were. Okay. So the more interesting evaluations of HomeOS that we did actually are not about sort of the particular performance. I think performance is good enough for building most applications that I can think of in the home. But we did both a programmability study and a usability study. I'm going to omit the usability study results from here, but if you want to talk to me later about them, I'm happy to talk to them. But the programmability study, we actually had 10 students and developers come in and try their hand at writing an application for HomeOS. And we asked, they had no prior experience with HomeOS. We asked them to write one of two applications, either a custom lights per user application, which asked users to look for rooms that had cameras and lights, and then see if it recognized any faces in the camera, and if it did, set the lights to the appropriate level in that room. And the music follows the lights application, which I described previously. And 8 out of the 10 people finished this in less than 2 hours. And the 2 people that didn't finish, one person spent their time building a GUI for about an hour before actually trying to accomplish the task that we asked them to complete. And the second person had a misunderstanding about the driver model for an extended period of time without asking for any help, and also spent sort of an hour doing nothing. And so the claim is not that 80% of all applications for HomeOS can be built in 2 hours, but rather that reasonable developers can build interesting stuff in a very short time frame with no prior experience with the system. And so I think this is pretty compelling evidence that this approach has legs in terms of making it easy for developers to build interesting applications in the home quickly. So in summary, I really do feel like homes are where phones were 5 years ago. There's a huge amount of technology floating around in them, and we haven't really figured out how to harness it yet. I think with the right infrastructure, we could really create a similar wave of innovation where suddenly we can rapidly expose all kinds of new functionality and have it shift the way we think about our daily lives. And we're in the process of working with researchers at a bunch of universities in order to try and get this around and actually having people using it. And as of about a month ago, it's running in a real person's house that we didn't ask them to run it. They actually came to us and said they wanted to have a security system that was made cheaply out of these parts. And so we did that. So it's real in whatever sense that means it's real. So I think this is the right approach, and I really do think that we could create a huge difference by getting this out there.
Your phone analogy, like, so the Windows Mobile was there, and it was programmable before the current wave of innovation that we see now. So
did you use it?
So I'm going to ask you. I used it. Yes. So what was missing?
So I can tell you what people inside Microsoft have told me as to what was missing with Windows Mobile. I think that what was missing was sort of a good experience end-to-end across the system. And what I've been told about why that is it's in part because the hardware was very varied, which is what radically informed the design of Windows 7 with a sort of specified set of chassis and things like that to make sure that the performance was sufficient in order to get a nice interface and experience across the whole system. And that difference made that sort of getting one set of hardware that gave you consistent and sort of expected behavior was a big part.
Exactly, I think where you're headed, which is homes don't have that property, right? You've just made the argument that your home doesn't have a consistent set of hardware.
Yes.
Because if it did, then the security company installed it.
Yeah. So I think that that's true, but there's a caveat which makes this problem a little bit easier, which is that HomeOS itself is probably going to run on a dedicated appliance, which is either a PC or your Xbox set-top box. And so that could have the property, which is that you have one consistent set of hardware that actually provides reasonable expected behavior.
Well, except the apps are going to expect some suite of devices. I mean, when somebody writes a phone app, they expect that there'll be some subset of devices.
And we provide mechanisms to specify that expected support and actually check for it in a home. And so it's true that you're probably, if you want to make this work in practice in the real, you would want to come up with applications that had relatively small number of requirements at first that most homes had. And I think there is kind of a core set of things like that. You can imagine the multimedia experience in your home being something that probably the hooks for are in many homes. And then from there, moving out towards other things. You can buy a wireless controlled light switch for $20 or $30 right now. Now that's as compared to $2 for a regular one. If you didn't have HomeOS already in your home, you probably wouldn't be willing to pay the overhead. But if you already had something there for another reason, it would probably be worth it to you. I mean, it's only $20. But I think you're absolutely right.
I feel, at least not right now, maybe it will change in the future, is that very few homes have a PC running 24/7. I mean, what's your position on that? I mean, even people sitting here, how many people have their PC running 24/7? I don't.
This is not a good sample. So this is the wrong sample. So I think I think there is some validity to that. I think there is some validity to that, but I feel like integrating this with some other sort of always on or always standby appliance, like an Xbox or something else. I mean, getting something which can go to sleep and wake up on demand, and it doesn't seem like the really hard problem here. There's lots of good work around that. I'll take your question. At some point, I should move on, but.
Oh, sorry.
Oh no! There's a whole there's a whole second half to the talk, which will be fun.
You talked about the problem of access control, and your principles seem to be combination of user and application.
Yes.
Yeah. How are you going to do authentication? Because that seems like something that, how do you identify the user when the mechanisms for identifying the user vary hugely on all the different
our imagination is that most rules will actually specify star for user, and that access will actually be granted on behalf of an application. And that for the ones which don't, we can use. We haven't really spent a bunch of time thinking about how you authenticate users. We imagine username and password is good in some instances. Using your cell phone, which you're accessing it from, is useful in other instances. We're sort of getting around that. But we imagine that a bunch of things like if you can get access to the music player app inside the house, we don't really care who you are. We're just going, so physical access is something which buys you a lot. Which is to say, if the only displays which you're going to render are inside the house. Just saying that music player app is allowed to have access to the speakers is probably sufficient.
Right, but that would restrict the kind of policies that the users can express. They can't express every arbitrary combination of user and app. You can't figure out who the user is.
Yeah, although I think
these different domains for, in other words, the way that even the language you use to describe a user is different for your on the phone versus voice or face or something. So it's hard to imagine the abstractions all bubbling up to a single API at the OS level. It's not just going to be a GUID, I guess is what I'm saying.
I think the combination of application and the applications getting permission to devices, followed by, if for whatever reason you need to do something which just the application doesn't have permissions to do, escalating that and asking you to authenticate yourself, either by, pressing accept on your phone or unlocking it under username and password. I think that probably would handle a bunch of this stuff in the home. I guess, and having talked and gone through what people say about how they use their technology in their homes, it leads me to think that would get you a long way towards there. Okay, sure.
So I find the HomeOS very similar to traditional OS, where you have device driver, you have services, and you can program access each device and write application against each service. So what's unique about the HomeOS compared to the traditional OS?
I think the differences in access control I mentioned earlier are sort of one piece, which is that maybe for reasons that just have to do with historical reasons, you don't have applications as priorities. Time tends not to be a role in access control decisions, and you're less concerned. And then there's been much less effort about convincing people that you've configured it correctly and actually letting people interact with the decisions that they've made about the access which you've done. I think that's one part of it. I think the other part of it is simply the standardization model for how it is that you standardize the interface which you write applications against. So the model in a traditional OS today, right, is that Microsoft says this is the interface to a hard drive, and it looks like this, and your file system, or this is the interface to a camera, and it looks like this. And there isn't sort of a first-order way to shift that easily on a device vendor and actually expose that functionality up to developers. And so this focusing on sort of a more dynamic interface between devices and applications is also, I think, pretty different from how commodity OSs are built today. Cool. So now that I've talked about HomeOS for a while, and I'm happy to take questions more, I think I'm going to meet with a bunch of you later on during the days. I want to talk about ETTM, which is about sort of how do you manage an enterprise network in a different and more scalable way. So before I went to grad school for all the power and money that a PhD gets you, I worked IT and I ran networks for people. And so I have some idea of what it is that I want from an enterprise network in terms of what I want it to do. And this is sort of, I'm not necessarily a complete list, but a list of a bunch of things I think you would absolutely want from your network. You probably want a NAT, whether it's just to share a few IP addresses among a lot of computers, or these days to deal with the IPv4 exhaustion. You're going to want some kind of firewall to keep the bad guys out. Traffic prioritization to make sure that BitTorrent traffic and bulk downloads don't interfere with your video conferences. A transparent web cache for all the nice things that we love web caches for. Remote access, so that way people can work from home. And I want some kind of pervasive intrusion detection so that we can tell when something has gone wonky inside of your network. In order to do this today, you have to buy a bunch of proprietary boxes and put them in your network. You have to buy a firewall. You have to buy some kind of IDS. If you're lucky, they might be bulked together. The NAT might be there too, but you probably want a different one. Different people have different specializations. This is sort of expensive, but not only is it expensive, as you scale it out and you buy multiple of these in order to scale, it's potentially inconsistent. It's inextensible. You have to sort of hope that somebody's built the box that you want already. And it doesn't scale up automatically, which is that if you add twice as many hosts, you have to hope that the boxes are either under provisioned, or you have to buy new ones. And so just to give you an example of these limitations, I'm going to talk about intrusion detection. And you can start to think about how this would apply to the other applications that I talked about. But intrusion detection is typically deployed at the edge of your network today. You can imagine the intrusion detection box being this red firewall in the middle of your network. And sort of as traffic comes in, it's going to classify some traffic as good and nothing needs to worry about. Other traffic is going to be classified as attacks. It's actually going to raise an alarm, let some IT person know that this might be an attack, but we're going to go check on that host. It might even actually block the traffic. But because it's deployed only, and it can even do things like detect outgoing traffic and say, oh, it looks like somebody inside is launching an attack outside. That host might be evil. We should go check if it's infected. But because it's deployed only at the edge of the network, it's difficult to catch internal threats. So if you have sort of a host inside your network attach another host inside your network, it's often difficult to try and catch these things. And you might say, well, this is just a problem of increased deployment. Buy a couple more boxes and drop them in. But not only is that kind of expensive just because now you have a bunch of these different boxes, but most of these services are stateful. They actually require, and so this requires coordination amongst these devices, which is difficult or impossible depending on whether the devices you happen to be buying support this. And so this sort of ends up being kind of hard to provide the pervasive intrusion detection you'd really like to have in a network today. And so we're going to propose sort of a radically different approach for how you might try and get the pervasive network services that we want in networks. And we call this approach an end to the middle. And this is sort of evoking the end-to-end argument of pushing functionality back to the edge and leaving the core as sort of a simple, straightforward thing, which basically just forwards packets. And it's based on the realization that we don't need physically centralized hardware to make logically centralized decisions. And we can actually implement the network functionality we want as virtual middle boxes, running as distributed software across the PCs in the network. And so to give you an idea of how this might work, let's return to the intrusion detection example. So let's assume that we have a trusted shim at each host that's monitoring and giving us control over the traffic which arrives there and leaves. This gives us pervasive monitoring, so when somebody actually starts to launch an attack inside your network, you can detect that they're doing something strange. And it also gives you the ability to identify that they're probably infected and actually quarantine that host, either at that particular host or at the other host, blocking traffic that comes from them. And so this is sort of going to be the approach that we take in ETTM. And there's a bunch of challenges, which I'll obviously go through and explain how it is that we overcome them. But first, I just want to state a little bit about what we're assuming in order to go build this. So we're assuming that we're operating an enterprise network, not a transit network, not a data center, not a home network. So we have some kind of IT staff that wants to accomplish goals. It's really about trying to service the actual hosts that are on the network, not trying to transit a bunch of traffic. And it's not in a data center, so these are actual users using these hosts. It's a single administrative domain. It's about giving one network administrator or a network staff more control at lower cost of their network.
Is Microsoft a single administrative domain?
Probably not, right? But probably Microsoft Research is one domain, and you might even do it per building. But I think that there's most organizations have a pretty good idea of what a network administrative domain is and isn't at this point. Which is sort of who has control over the network, right? Who actually administers the switches and the hardware. Does that make sense?
Yeah, I was just trying to see what your underlying assumption is about single administrative domain.
My underlying assumption about single administrative domain is just that I'm not trying to merge conflicting policies or anything like that. That there's going to be one set of policy which is actually agreed upon by somebody, and that is it's being implemented, as opposed to trying to figure out how to sort of negotiate policy differences and find the lowest common denominator kind of thing. That's what I mean. So I'm going to make a set of assumptions about hosts, in particular that they have trusted computing hardware in them, that they are multi-cores, and that they're virtualized. And I'm going to assume that switches provide some form of access control. Now, this might seem like a lot of assumptions to make about hardware, but fortunately, the assumptions I make about hosts are increasingly true of commodity PCs today. And the assumption that switches provide access control can be provided by either 802.1x, which is commonly supported on commodity networking gear today, or by OpenFlow, which is an emerging standard for programmable networking hardware.
Can you be more specific about what you mean by trusted computing hardware? Just mean a TPM?
Yeah, for the purposes of what we've built, it's a TPM. I can imagine using other. In fact, I can imagine other trusted computing hardware being much more useful. But for the purposes of this, what we built was on top of TPMs.
Do you consider ETTM as a replacement to the current mid boxes, or it's like a complementary to the existing?
Are you asking me in my academic researcher hat, or how I would actually get it to work in practice on a real network in the short term hat?
That answered the question right there.
I think that in the long run, it would be interesting, and you might do hardware acceleration for some tasks that require it over time. In practice, if you want to get this working today, you would probably, you'd probably start off with providing the services that are hard to provide in a reasonable way or reasonable cost on middle boxes, and slowly shift it out. Nothing's going to happen overnight. The other thing which I can imagine happening is for small and medium businesses that affording all of the sets of hardware that provide the properties you actually want for your network is difficult, especially, and providing people that can actually run them is also difficult. And so the idea that you might provide like a software solution that they could go get for a reasonable cost that would provide them the properties they wanted seems like they might be able to get almost all of their functionality from this kind of system.
Yeah, but there are some benefits of using mid boxes rather than doing everything on endpoints, right? Even if it completely works, you have all the hardware, so you always want to stop the unwanted traffic as early as possible.
But what's earlier than the host which is sending the traffic? Like that's actually a place where.
From exterior, for example, you don't use the air traffic to enter your network to hit your host.
Fair enough.
Right. So you still need all the mid boxes, all the firewalls to stop the traffic.
Not if you believe the argument that Collins virtualized virtual mid boxes are robust. If you believe they're robust, then it doesn't matter if the
Well, so his claim is like network bandwidth, right? How are you going to protect network bandwidth?
I see. Well, there's no switches you're going to do for you?
Yeah, you could. So you can imagine having some small piece. And I haven't spent as much time thinking about this as I would like. If you end up with OpenFlow boxes and they implement the new extension to the spec, then you can actually do things like rate limiting. And you might imagine that rate limiting is something you want the network to natively expose and allow you to actually use. So there is a question about what functionality you do want to eventually end up within the network. And for the purposes of this talk, I'm going to assume basically it's just packet forwarding and turning ports on and off. You can imagine slightly extending that if it got you significant benefits in terms of manageability or performance.
Virtualization seems somewhat of a kludge because I don't quite see why you actually need it, and it definitely comes at performance penalty even if hosts do support it.
Why don't you ask that question again after I get to that point, and you can explain to me why it is that I don't need it. So we have 3 key goals in building HTTM. The first is we want to make it easy to extend network functionality. We want to make it easy for people to build applications that give them the functionality they want on their networks, or go deploy something somebody else has built and actually get that. Second goal is, in order to do this, we're going to have one platform with simple APIs that enables people to build the applications as well as go deploy them on their network. Second, we want to automatically scale with network demand. And in order to do this, we're going to run management on already present hosts in the network. So we're actually going to run this stuff on top of the hosts which come into your network. It means they bring their own management resources with them. And lastly, if you're going to run management tasks on people's machines, you don't want Bob and accounting's machine going down to take down your network. So you need to function pervasively, consistently, and fault tolerantly in the face of sort of this distributed implementation. And to do this, we're going to use standard distributed systems techniques included, and we're going to use in particular a consensus algorithm called Paxos. And I'm going to describe how we use it a little bit later.
For your first bullet, where do you expect the new functionality to run? Is it your virtualized, secure, cyber?
Ask that question in 3 slides if you don't understand. So there's a bunch of challenges. 2 slides if you don't understand. There's a bunch of challenges that come up when you sort of propose this approach. I mean, the first and foremost is, can we even trust commodity PCs to faithfully carry out network management tasks? It's pretty clear. I mean, existing commodity OSs are famous for getting infected and famous for having users that are selfish and will configure them in whatever way gives them the best service.
That's why we have firewalls.
Yes. Yes.
I mean, if we can trust them, then we wouldn't need to put them behind a firewall to protect them because they're tenured.
Yes. So, yes. But there are reasons why it is that you might be able to trust at least a subset of what they do. And I'll explain that second. So can users, commodities, actually quickly make consistent decisions? Can we make them fast enough? And lastly, how can we enable developers and administrators to build new applications and get them out on networks easily? And so I'm going to address sort of each of these challenges and in the process build up the architecture of a single machine of what it's going to look like in an ETTM's network. So the first question is, can we trust PCs? And the answer is, as John said, I think sort of obviously not in the canonical way you run them. Commodity OSs aren't up to date. They get infected. Users are selfish and will configure them however they want to configure them in order to get the best performance. And so you might throw a buzzword at the problem and say virtualization. Virtualization is what we use to solve problems. And a hypervisor in this case actually does help you. It gives you a point of control, something that's less likely to be infected. And it does actually give you a place where you can talk about stopping traffic, which Commodity OS sends. But there's no way to actually tell if a hypervisor is running on a host. It'll lie to you if it gets it better service. And so we actually extend the hypervisor with support for a TPM, which lets us actually get an attestation from the machine which says, in fact, it did boot the given hypervisor. We can actually tell that it booted that. But that's not quite enough, because just knowing that it's running what you want or not doesn't help you if you can't keep it off of your network if it isn't running what you want. And so we actually extend the 802.1x network authorization protocol in order to basically deny access to hosts until they've sent us an attestation that they're running the particular software stack that we trust. And even that's not quite enough. We don't really want to stick all of the functionality inside the hypervisor where we add to bloat and add to what we have to trust in order to keep things isolated. Instead, we're going to run our management tasks inside of an attested execution environment. I think this answers your question, which is a specialized virtual machine on top of the hypervisor, which is used to both filter traffic as it comes in and out of the host, and also to run any other network management tasks that you might want to run in a trustworthy manner.
Did you just claim that putting these applications inside that VM instead of inside the VMM takes them out of the trusted computing base?
So no, it doesn't take them out of the trusted computing base. It does give you another layer, which you sort of have to work, which you don't have to. So
trusted or not, buddy?
It's trusted. So it's trusted from the point of view of the network. So right, the network, but it's not trusted from the point of view of the commodity OS, which is to say, now you've given the user some assertions.
Okay, thank you.
So it depends trusted from whose point of view. Also, this model makes it easier to be portable across different hypervisors, which is critical if you want this to actually work.
So I think this sort of goes back to Ming's question, which is that if your goal is to, it's not safe unless everything is sort of going through a filter, which is why usually people put a firewall at the choke point. But what you're doing is saying, well, we're going to distribute the choke point, so to make sure that the attack surface is no different, we have to make sure that a little piece of the firewall is on every host.
Yes.
But then, how do you plug in, printers or embedded devices or anything else that doesn't do that? I mean,
so the short answer to that, which I'll explain in a bit, is that you can create a secure tunnel you can run a test execution environment on some other commodity host that's been vetted, and you can create a secure rate-limited tunnel to it across your network. And that's a pretty reasonable thing to expect of the switches in your network, to be able to forward traffic that way.
So imagine that there was a bug in the hypervisor that allowed the correct designed hypervisor to be compromised. I know this is inconceivable, but say it happened. What do you do at that point? Is it over?
Let me answer your question with a question. What if there was a bug that gave you control of things in Cisco's iOS that gave you access to the network? Is it game over? And so, yes. I mean, the answer is yes, but I don't think it's any different. In fact, the last time I checked, I think this is 2009. In 2009, Cisco iOS had something like 20% more vulnerability days than Windows.
There's an order of magnitude more boxes that you've got to update.
That's exactly.
We're pretty good at updating. Updating PCs is something we're pretty good at, especially inside a corporate environment, right?
So what makes
I think it's easier to
what makes updating hard is when the update targets are not the number of update targets, but the heterogeneity of them. And his argument is, well, if the piece you're updating is the same everywhere, getting them all updated isn't particularly harder than getting all of your Cisco boxes updated.
But to do an update here, I mean, if you have a clever hack, you've now got a validly signed thing that behaves badly. And so in order to fix that, you've got to go out and touch the TPMs on all of the machines in your network to tell it that old signature isn't good anymore. That's a part of the problem.
So this is actually something which you could fix with this. This is what's the same properties upgrading your iOS boxes. You need to deploy some. So we actually store the information about what's a valid signature and what isn't. Actually in one place on the network, and so you just need to update that file and then push out an invalidation to sort of the people that have already sort of kick everybody off the network, if that makes sense.
Yeah, but if I'm a malefactor and I now own the network interface on there, I'm not going to look at your revocation list anymore.
Oh, but the switch will. That's the assumption, I guess. Is that so if you break that and you break the switch, so that way the switch doesn't listen, it's true. Then you've taken over everything that I have.
Switch tell.
So the switch uses 802.1x, right? So we can actually push out a signed, close the Ethernet port for all devices and require everybody to reauthorize themselves.
But I thought the model was that you were trusting that it was running that hypervisor because the TPM said it was.
So yes, but then you kicked me out of my model where I can do that. You said the hypervisor is broken, and I'm giving you what you would do.
Because it will be. You know it is.
But is that any different from the switches inside your network being compromised? I mean, I guess I feel like it's a slightly different trust model. It's not. I'm not convinced that it's actually concretely different, if that makes sense. Which is to say that switches can be compromised as well, and we don't seem to worry about that. I don't know why.
It's easy to get the hosts.
Well, yeah, I think the reason why is because switches have a very, very isolated control path versus data path, which is that usually packets just pass through switches,
and usually packets just pass through hypervisors too.
No. What I'm saying is that the host contains the hypervisor code. In other words, if you own the host, then you can start writing bits into the hypervisor, presumably if there's this hypothetical weakness. Yeah. Whereas with switches, you can't even talk to them. I mean, they don't even have externally visible IP addresses, whereas hosts all do.
I'm sure they do.
That's
switches all have management interfaces.
Yeah,
they have management interfaces.
I guess my claim is that in practice, switches have just as many vulnerabilities, just as long windows opening as commodity OSs, actually slightly worse. We just don't worry about it, and I don't know why we don't worry about it. Maybe I should put a slide in my talk of you should be worrying about your switches and your routers. Yeah. I think the actual reason why they don't get compromised as much is because they have less value, which is to say that end hosts have value in the resources which you can steal from them, and compromising a switch is much harder to get value out of. But in that sense, the commodity OS would be the target of the thing, and this hypervisor and the AE would also still be a relatively low value. Except as a way to get to the commodity OS. The hypervisor
has at least as much value as the commodity OS, right?
Because they can replace it.
So with that long digression, these are all useful things and certainly conversations I've had. It'd be interesting to go talk about. I actually have another separate side project I'd like to do of TPMs for network hardware, which is that we shouldn't just trust network hardware because it says it's trustworthy. We should actually try and do similar stuff to this and get us also an extra layer. So secondly, can commodity PCs consistently make quick decisions? I'm going to use Paxos to do this, and I'll talk about the particular interface we exposed to Paxos, but Bill will talk to you about how you can make Paxos fast if you want to know. I think he knows more than I do. And lastly, how can we enable developers and administrators to build applications on top of this model and actually get them out on your network? And so we have an interface for filters, or how we give applications control over the packets that flow in and out. And we have a micro virtual router that invokes the filters on the packet flows. And the consensus API combined with this filter micro virtual router API is the API which you actually write network services against. And so you end up with a binary that you can go actually distribute to people, and it works. And so I'm going to talk a little bit about sort of each of these challenges and the pieces of technology that we built in a bit, including about how we do trusted authorization and how we do legacy hosts. Go ahead.
The tested execution environment is Linux. Is that some like stripped down library?
It's Ubuntu server at the moment. It's just some VM that has a reasonable way to do network processing across what the hypervisor sees. It happens to be Linux because that's what it was easy for me to work in when I was building it. There's nothing special about Linux that I rely on. And you can imagine building a really stripped down something to do this that basically...
That is actually a challenge. I mean, how to make sure it's stripped down, secure, and still easier to debug. Right?
That would be a lot of fun to work on.
It's not addressed
Even without the easy develop part, it's still hard.
So right now it's about 400 megabytes. I'd like it to be about 10. And actually, I think it might be interesting to talk to. I guess it's not quite related to the drawbridge stuff, but it's
because
similar.
You as your challenge. I thought you tried to solve this problem, but obviously you solve from different angle.
Okay. So the way trusted authorization works in this is we have a switch. The 802.1x protocol causes the switch when it sees new hosts on it to actually go and say, you're a new host. I'm not giving you access until you tell me who you are and why I should have access. That takes about 50 milliseconds to figure that out. And you can fix that by sending a request explicitly, but if you think that you're attached to that. But once you've done that, the host then responds. And in this case, we've overridden it so that way the identity which it uses is the public key that it's actually going to sign the attestations with, rather than any normal identity that you would use in 802.1x and EAP. That's then forwarded to the verification server. And the verification server you can imagine as being some dedicated box. Or you can just, and what we do is run it inside of a tested execution environment on another host. So you don't actually need any dedicated hardware to do this if you have other hosts that are up. And at which point the verification will serve with a challenge nonce to make sure that whatever attestation it gets back is fresh. And this takes about 20 milliseconds for the verification server. We use the Open Radius server, and it's just a little bit slow. But that doesn't really matter because signing the registers that specify the state is even slower. It takes about a second to do it on the hardware we have. My understanding is that there's some newer hardware that reduces that by a factor of 2-ish. But this is just because TPMs, nobody cares about performance, and nobody's optimized it. It's likely to be in the future this will either migrate into the CPU or simply have a slightly faster processor, and this is just going to go away. Then the verification server and the host will negotiate any policies or new software that needs to be deployed. And finally, you'll open up the port. And all in all, this takes about a second, a little bit more. And this can be overlaid with commodity OS boot time, making it basically trivial. And in the future, as I said, sort of if TPMs are actually used, they'll get much faster. And this will be something on the order of how long it would take you to get an IP address anyway to get out onto a network. I said I would talk about legacy hosts. So let's talk about hosts that either don't want to or can't run their own tested execution environment. So they're going to show up on your network, try to connect, and be denied because they're not running the software you asked them to do. The nice thing is that since the AEs are sort of virtual objects, they need to actually run on the device whose traffic they're filtering. So we can instantiate WASUN somewhere else in the network. And as long as we create a secure rate-limited tunnel that only goes to that AE, we can then actually give that host access to the network. And so this enables you to get printers that are protected and actually have their traffic filtered, the iPads, whatever. Xboxes. And so this sort of does mean that you can actually have everything on your network. You don't need to have all devices be able to run this kind of stuff. And actually, when I started off, I thought this was going to be a real problem because everything's going to be a phone and it's not going to have virtualization or trusted computing hardware. But in the 2 years that I've been working on this project, phones have started to get virtualization and trusted computing hardware in them. And so you might actually even be able to do this on phones natively. And I think that would be kind of interesting to go and play around with. So in order to have consistent state that applications run against, we use a consistent shared table abstraction. So the table consists of one row per application, and each cell is the result of a Paxos round, which is to say that each cell is consistently agreed upon. Also, the ordering of the cells within a row is agreed upon. And so this way you can have sort of, everybody sees a prefix of every row. In between rows, we don't do any consistency. So if an application wants to have consistency across two rows, they need to implement that. But this gives us scalability because each row is thus actually independent and can make progress. For those of you that are really familiar with Paxos, you'll realize that Paxos only makes progress as long as the majority of the nodes are up. If you're talking about running on commodity hardware, it's possible that a majority of your nodes could fail simultaneously. Imagine, a building goes out, or power go out, or a floor goes out. And so in order to deal with this, we allow for unsafe progress explicitly. So for instance, if the NAT application sees that more than the majority of the nodes go down, it can actually say that it would like to fork, by fiat declare a new Paxos group, which is the set of up nodes right now, and continue to make a separate set of safe progress here. And then later on, we might have to merge any conflicts. And while in theory, merging these conflicts is, very difficult, in practice for many things like a NAT, it's actually relatively straightforward. You can go through and look and say, oh, these two external port and IP address allocations are different, send a TCP reset in each direction or start blocking traffic.
I think I missed a step, and I will risk an embarrassing question because maybe other people will also miss this step. What is it that you're trying to keep consistent using Paxos? In other words, is it just to make sure the policy gets
so one of the features that I give to applications is a Paxos-backed hash table, things like that. So you can agree upon anything you want. In particular, I've used it to build data structures that are sort of snapshots of some recent point in time.
So why do you need a hash?
So for instance, imagine that you want to keep your network address translation table consistent, so that way you know that IP address 1.2.3.4 port 50 isn't assigned to two different connections. So the only way to do that is to know what the other allocations are, and so you can use this to build up a table of externally visible addresses to internally visible addresses, and know that you haven't double assigned something, and know that it won't go away if a host drops.
Controller at all? It's all tones distributed, or in other words, DHCP manages this
essentially
without.
Sure, and in practice, in a common case, we use leader Paxos, and so that's effectively what we do. We just use this as a way to be resilient against that leader failing as well, and also have consistent state in case, some.
Question a little bit different way. At what point were you sitting writing code and you reached a problem and you said, oh, we can't solve this without distributed agreement, so we need to put Paxos in? I'm not quite clear on that.
So imagine that you're writing a NAT in a distributed fashion, right? And you want to assign, and you have a new connection, and you want to assign it an externally visible IP address and port. So now, if we assume that there's some designated leader, we can just, a DHCP server, we can go out and just ask for it, and they'll come back and do it. Now, if you want to be resilient against that person going down because they're also a commodity host, you need some replication strategy. And you could use two-phase commit. You could use, and that has advantages and disadvantages with respect to Paxos. You could use something else. We chose to use Paxos because it doesn't impose much overhead over other replication strategies, and it buys you a lot.
Algorithm to pick IP addresses, DHCP is completely distributed, like automatic IP assignment.
I think DHCP is actually the wrong analogy here. What's happening is I'm instantiating a new temporary port for my connection, and you do too because you start a new connection.
What's to stop us from
How do I make sure that we don't pick the same port?
So there is, like for IP assignment, there is an algorithm basically, there is a standard.
No,
you pick IP and then you announce it, and then everyone says, okay.
So in a NAT, imagine you have a limited pool of some application. So if you want to do ephemeral assignment of ports in this case, you have to have some consistent way to assign resources to people in your network, right? And you can do that with a central person. If that person fails, you need some replication strategy to make sure you don't lose the configuration data. And Paxos is basically as fast as any stupid replication system you can do, and it has a lot of better features than you get from other replication things. So applications can choose to be always safe and not always live, or they can choose to be explicitly live with one particular boundary at which something can go wrong, which is to say that you know that internally in this timeline it's consistent, and internally in this timeline it's consistent, and that's much better than having no guarantees about anything afterwards. So it has some.
Right, and there's a theorem that says you can't do any better than that, so you really can't ask him to do better than that.
No, but if your programming model is, hey, everything's safe except when it's not, then why bother providing safety? I guess that's what I'm trying to understand.
So you can choose to say everything's safe and just not be live if the majority of the hosts go down, if that's what you want. Or you can choose to say that I'll be safe for this period of time and I'll be safe for this period of time, and I will have to explicitly know that you could at one point in time end up with two timelines that are internally consistent but need to be merged, and that's pretty clear. Okay. And so I think that's the idea that you could potentially have two timelines that are internally consistent but need to be merged is a lot different than you could have arbitrary bad differences between your timelines. So it's not quite as nice as having one timeline, but it's a lot better than the alternative.
So, it's 11:40 already, so I'm going to ask everybody what questions unless it's a really critical one.
I'll ask you when I see you in the afternoon.
So,
I don't get it.
Sorry, yeah.
And then eventually, once you've merged all the changes back in, you can actually garbage collect this row and it goes away. In order to actually give people access to the flows that go into and out of hosts, we have a micro virtual router which interposes on individual traffic. We have a hybrid implementation. One part of it uses Open vSwitch, which gives us line speed up to a couple gigabits, but only has open flow commands, so it's really only for packet header operations. So NAT works really well in this environment. Deep packet inspection doesn't. Then we have a separate implementation built on top of IP tables, which actually gives you the full packet, lets you write your filters in C++. And this actually, lets you build things like deep packet inspection and do, HTTP caching on content and all of this good stuff. The filters themselves have a relatively straightforward API, and this is actually what you write stuff against. These first 5 functions are really just metadata about when the micro virtual router should run the filter, on what packets, and in what order. And these last 3 are really the ones where you actually do things where you can filter, capture, delay, rewrite, drop, and inject packets. And we actually have separate versions of these when you use headers versus when you don't use headers, so that we can tell which particular instantiation of the micro virtual router to send the filter off to. And we also periodically call an upkeep function on these filters in order to be able to go out there and make changes, update state, and collect other things. So before I go into evaluation stuff, I'm just going to go through one example where we put all these pieces together and show how they work in practice to implement a network address translator. So on the left here, we have a particular host. On the right, we have the table for the NAT. And for those of you, just a quick introduction of how a NAT works, for those of you that don't know what it shares one IP address or a few IP addresses among a larger number of hosts. And traditionally, it does this by being in a centralized location, like this router, where it can actually see new flows, make the mappings when it needs to, and apply those mappings to traffic as they come back and forth. So instead, in the ETTM implementation, when a new flow gets created in the commodity OS in an application, it gets sent out, and the hypervisor will forward it over to the attested execution environment, where the micro virtual router will say, oh, it needs to be natted, so we're going to send it up to the NAT filter. The NAT filter will note that it's a new flow, and so we actually need a new mapping. So it will request a new mapping from the distributed consensus algorithm. This will actually go out and talk to all the other hosts on the network, or whoever has participated in the consensus algorithm. And this will run around, eventually agreeing on some mapping, in this case, C maps to D. This result will be communicated back to the host, which is actually sending the packet. And the mapping can be returned up. The packet can be rewritten according to the mapping and sent out to the general internet. And then later on, when a packet according to that flow comes back in, it can actually it gets routed up to the NAT filter and can be rewritten without any consensus operation needed because it has the mapping. Yes?
How does it get routed to the right?
I have 3 different implementations of how that works right now. One of them assumes OpenFlow, and we actually install the routes inside the network. Another one uses...
You're installing...
You install hints inside the network as to how to route packets. And if they don't match, then the OpenFlow controller, which is us, gets notified, and we can go back and read.
You just built a NAT then?
Yeah.
That's exactly what
well, no, not necessarily, because a NAT has hard state, and we don't. So if a NAT box got reset, then the connection would break. Whereas if a switch gets reset, the connection is still live. Yes.
This is the control half of it.
Yeah. So The second implementation, we actually spoof ARPs for the global IP address to be the broadcast MAC address, which is a horrible abuse of the way networks work, but actually works pretty well in practice.
As long as you're not sharing IPs.
As long as no, the externally visible IP address. We ARP to the externally visible IP address with the MAC address, the broadcast MAC address. So everybody receives all traffic destined to the global IP address, and just only the person who deserves it should actually accept it. And that's a horrible use of it. It does work. It works pretty well, actually. And the last thing we do is we just rotate the IP address across hosts. We actually just basically make one of them a NAT. So there's a bunch of different ways of getting around this. But yeah, you're right. That it's kind of tricky. And you actually caught this, whereas I think only one person in NSCI caught the fact that that was sneaky.
What else are you sneaking by?
That's actually detailed in the paper pretty extensively. It was just omitted because it's a painful thing to have to go through when people are explaining distributed consensus was probably a bad move in the talk where people might understand it. Never mind getting into the details of low-level NATs. So we've implemented a whole bunch of stuff on top of this. We've implemented a NAT, a deep packet inspection, web cache, traffic prioritization, a worm scan detector, a generic firewall. Most of them are only a couple hundred lines of code on top of this. And so we think it's pretty easy to build a bunch of interesting stuff on top of it. And in fact, I'm going to talk a little bit about the traffic prioritization stuff later on, which is actually one of the harder things to go build on top of this. But really, you might be wondering, isn't this going to suck in terms of performance? We're running this on commodity hardware at the edge of the network rather than running it on these custom ASICs. So really, I'm going to focus my evaluation on sort of the performance of the underlying pieces.
The only applications that require distributed consistency?
No, they all do.
Anything else requires
so deep packet inspection doesn't. The worm scan detection actually needs to share views of traffic sketches across it in order to be able to say this host is talking to a lot of other hosts, so therefore it's probably doing something bad. The firewall needs to be able. The firewall that we've built is not stateful, but you can imagine one that is. The traffic prioritization actually does per round trip time, per flow, bandwidth reservations in order to make sure that we're allocating bandwidth according to some policy. So most of these involve some form of distributed consensus.
It's okay.
It's a matter of sharing information instead of like they have to reach a consensus. That's
so consensus doesn't mean everybody gets equal power. Consensus just means everybody eventually decides the same thing. Sorry, this is the difference between what we say consensus means in normal world and what consensus means in a distributed systems world. In the real world, consensus means that we all get together and we agree and it's happy and sort of it's a egalitarian process. Consensus in a distributed systems world means that everybody will make the same decision. It might have been decided by a dictator that says everything is exactly what I say, but it will just be the same decision everywhere.
It only really means eventually they'll reach the same.
Yeah.
Because by distributed consensus is
maybe
possible.
So is consensus fast? The answer is yes, as long as you don't write to disk and you're making decisions in under a millisecond, you're doing decisions on a LAN, you can make fault-tolerant decisions in about a millisecond. Less if you're running on a smaller number of nodes, and if you sort of pick a subset of the nodes that is highly available and well-connected, this works really, really well and really fast. It's not the bottleneck that you might imagine it would be. So the second question you might ask is, well, does it scale? How many decisions can you make per second? How many new things can you do? And so depending on the group size, that's the number of people participating in consensus. We actually run that on a subset of the nodes. So you could have 500 computers, and you would have some core of 10 of them that are well connected and fast that you've decided run the consensus, and 10 is plenty for most reliability point of view. The trick is just to have enough so that way they don't go down often.
You don't want to run it on 500.
Yeah, you want to run it on some numbers between 5 and 20. I think Chubby is run on something like 13. So in terms of scalability, we can add somewhere between 1,700 and 8,000 cells to a row each second. And they're really good techniques for scaling this up if you want to scale it up. You can partition things. You can partition across applications. This just isn't going to be your Achilles heel in this kind of system.
Because your equivalent of 8,000 there, I was able to do 50,000 and write to disk just by making the code path slower.
Yes.
So.
Yeah. We haven't. So what we have written is like a few hundred lines of C. We haven't spent a ton of time optimizing this. So the next question you might ask is, do filters hurt performance? We're actually doing some packet processing on each packet as it leaves. So the first thing I want to note is sort of this is flow size on the x-axis, and this is the throughput on the y-axis. So for large flows, both using the NAT filter and not using the NAT filter, we hit the full gigabit per second. There's basically no difference. And in fact, for all flows bigger than 10 kilobytes, there is no difference between the two flows. And the only reason there's any difference for really short flows is because we are using a Paxos time to start off the round trip time, which slows down slow start for the first round. And this is actually two hosts in the same network. So the round trip time is actually about 180 microseconds. And we're imposing about a millisecond of delay before we make the connection. If you were having a real connection where the round trip time is about 30 milliseconds, this would be totally invisible. And so filters don't really seem to hurt performance much. And now you might be thinking, well, all I've talked about is really simple filters, things that run on one place. What about something more complicated, like trying to do bandwidth allocation, trying to actually do fair share bandwidth? So on this top graph, what you can see is what happens if you don't do anything and you have a big queue. So if you run BitTorrent while you're trying to make requests to Google.com, what you can see is that when you're not running BitTorrent, the queues are fine, everything's OK. Suddenly you start running BitTorrent, and it's going to fill the queues to capacity until it sees loss. And this is going to result in it taking basically as long as your queues are occasionally in order to make requests. In this case, like 10 seconds. And we didn't configure this that badly. And so in practice, what you'd like to do is something different. You'd like to be able to actually allocate bandwidth in a fair way so that way the BitTorrent connection couldn't blow your queues quite that badly. And so we actually implement a system where we make reservations for bandwidth. Every round trip time, each flow, actually we trigger a reservation that says, but I used this much bandwidth last time, I would like to get that much bandwidth again this time, and there's details in the paper, but in the end we basically don't allocate more bandwidth than we have. We know how much bandwidth we have in the access link, and the result is a much more stable latency because you're not blowing these queues hugely out of proportion. And the cool part about this is that it actually works. We can make per round trip time, per flow decisions, and actually go out and do bandwidth allocation in a distributed fashion on a network. And that's kind of surprising. I don't think many people would have thought you could do bandwidth allocation on end hosts in a consistent way and have it actually work.
And this works because your internal latency is a couple orders of magnitude better than your round trip latency of the internet.
Yes, essentially.
It is.
Yeah, because it is in practice. We haven't looked at how to extend this to wireless quite as much, and that might change some things because round trip times get to be kind of strange. But I have some ideas there. So in summary, enterprise network management today is sort of complex, it's expensive, and ultimately unsatisfying in providing the kind of properties that you actually want out of a network. And I would urge people to not consider Microsoft. Microsoft is the best managed enterprise network I have ever worked at. It is really well run. There are lots of places out there where it's just terrible, and people really struggle to get these things to work.
Do you think Microsoft's network is satisfying?
No. Well, so I used to work IT, and it used to drive me nuts because I knew what I needed to do in order to get the problem done, and I couldn't. And I just wanted to write code to make it happen. And so that's where this actually came from. This is, 7 years later, I come back. I want to write the code that makes the thing that I want to happen on the network happen. And so that's sort of what I mean by ultimately unsatisfying. So we propose a radically new approach. We implement network management as tasks, as software on end hosts. We make it easy to write in distributed applications for networks. We can manage the management resources scale with demand because they are the hosts that are coming onto your network. Tasks run pervasively, consistently, and tolerate faults sort of by design. We implemented a bunch of applications on top of this. Obviously, I'm not the first person to realize that you need to manage your networks. There's a lot of related work in network management. In particular, industry, including HP, IBM, and CA, have written tools. But these are mainly around visibility. They're sort of about what network links are up or down and how much traffic they're carrying. A bunch of other work has worked on how it is that you actually pick paths for packets across your network, but not really anything other than the particular paths that the packets are going to take. Other work, including from people that are currently in the room, focuses more on isolation, be it performance isolation or security isolation, but again, sort of not the pervasive nature of all the tasks you want to carry out in your network. And there's also been other work that involves end hosts, though usually sort of as a side piece to other network management. Network exception handlers sort of tries to use end hosts and certain exception conditions in order to be better. And system monitors tries to use end hosts in order to get visibility into the network, but again, not actually control. On the other end, there's been a lot of work on sort of programming networks of devices, kind of like things I did in the home. But it tends to be either focused on a specific domain or just be a couple of ideas that were tossed out there without an implementation or a very restricted programming environment. And other stuff, sort of monolithic systems, be they commercial or academic, tend to be either closed above, closed below, or both. And we really want to be open below to all possible devices that we might be able to get people to write our drivers for, and open above. And this sort of really distinguishes what it is that we've done here from other stuff. I have a bunch of other things I'd like to work on. The first is I'd really like to try and build a fully integrated programmable network. Something like HomeOS on the top for programming applications across the devices, and something like ETTM below, so that way you can actually talk about what's happening on your network, and actually have security policies that cross back and forth through it. Debugging and diagnosability seem like much easier if you have some knowledge of what the network is doing below. So I think marrying these two ideas actually has a lot of interesting things that will drop out of it. I'm really interested in home security and not your front door lock, although I also like to teach lockpicking, so I can do that. But homes are increasingly networked, increasingly wireless, and this poses a huge number of challenges for how we're going to make them secure, both from sort of the pure security model of how do you make these devices not easy to hack, but also how do you get users to express what they want to happen? I mean, right, we don't really have enterprise access control working in the enterprise today. And it's even worse in the home. You don't have anybody that's around. But it has some really cool advantages, because I'm not talking about some file on some server somewhere. I'm talking about that TV, that one over there in the corner. That's what we're talking about. And this gives people a mental model to root things in, where you might actually be able to solve some of these seemingly intractable problems in the home. I think that would be really cool to work on. And lastly, I'm interested in trying to build a peer-to-peer cloud. And you can imagine ETTM as a first step to getting there, in terms of suddenly you have a place where you can run code that you don't have, that you can trust will run correctly. But I think it provides them with some interesting alternate economic models for how it is that you run a cloud. Rather than the traditional sort of pay rent or watch ads, it allows for something more like the current model, which is that you go buy a computer, you drop it somewhere. That's how you get your computing resources. And this gives you that same model, potentially gives you similar things. There's a huge challenge in terms of reliability, performance. We don't really have the programming models correct yet for the cloud. We're just beginning to get that figured out, never mind for a cloud that's on end hosts. But I think it's cool. I don't quite know whether it would fit as a side piece to an existing cloud infrastructure that does certain things better, or its own particular thing for certain applications. So I'd like to thank my collaborators, my advisors, Tom and Arvind at UW, Dane, Hardeep, and Vyeko, who are really great undergrads who built real stuff. Undergrads are great. You should work with them if you get a chance. And my collaborators here at Microsoft who work with me on HomeOS. And so in conclusion, hope we convince you networks today are crucially important, but they're really hard to sort of extend, manage, and secure. We propose a new approach of turning the network sort of into a programmable software object, where we can solve these problems in software rather than in hardware. And we present 2 case studies for why it is that you might be able to do this and want to do this, in ETTM for enterprise networks and HomeOS for homes. And with that, I'm done 4 minutes early, and I can take a few questions. 27 minutes late. It was 10:30 to noon on my calendar.